Alright, so today we're going to be talking about indefinite integrals. And so let's just get right into it. So basically, thus far we've been dealing with evaluating integrals from having a lower limit and an upper limit f of x dx. And we have relied on kind of using um, intuition to find out what function capital F of, through the fundamental theorem of calculus, we knew that this is capital F of B minus capital F of A. And we have really relied on using like intuition and knowledge of derivatives to find out what the capital F function corresponds to. And so today we're going to finally introduce rules that map easily from capital F into F. And so hopefully that will help find out the integrals and evaluate them at a much faster rate. But what indefinite integrals are basically integrals without limits. So no limits. So we don't have any upper limit or lower limit, and we're just going to be given f of x times dx. And so when we evaluate this integral, we're essentially saying that this integral will correspond to some big f of x plus c. And again, this idea of plus c comes from the fact that we know through the fundamental theorem of calculus that if we were to take the derivative of this integral, we would get back this integrand, right? And the derivative of a constant, is always 0. So you can have any sort of constant over here, and that will be logically get you back f of x. That's where this plus c comes from, because you can have infinitely many integrals for some like indefinite value over here. And how do you arrive at like a specific value for a constant? That comes from the fact that if you were solving the initial value problem, so the IVP, and if you're given the derivative, right, you'd fit in the derivative into the integral, so you do like dy over dx. So this would be given to you, and then you do times dx. Again, this here is not a fraction, so these are two separate terms. That would give you some function big F of x plus c, and then you can solve for what that c is, because the initial value problem would also give you like y of some constant, let's just call it d, is equal to w. And then based on these two things, you can then solve for what value of c is. And then that will allow you to hone in on one specific value. So again, this is all pretty abstract. We dealt with a bunch of variables. Let's do a lot of examples, and so we can kind of get used to this idea. So example 1. Let's start with an easier one. Evaluate the integral from x squared minus 2x plus 5 dx. Now, we know that this is the same thing as x squared dx, and I'm trying to get to the very bare bones, times x dx plus the integral from 5 dx, right? And one thing that I forgot to mention is, remember, like I made a video on properties of definite integrals, and those properties carry over basically to indefinite integrals. Like when you're multiplying by a constant, the value of the integral also is scaled by that constant. And then the reason I can split it up is through the sum difference rule, and there's basically analogous sum difference rules in indefinite integrals as well. So having said that, let's evaluate this. We know that if you took the derivative of x cubed over 3, you'd get back x squared. And then we have to add a constant, so let's just call this plus c minus 1. So that's the evaluation of this integral. Now the evaluation of this integral is just negative 2 times x squared over 2, for similar reasons as why that was x cubed over 3, plus constant c2. Over here, we're just evaluating constants, so you have 5x plus c3. Or, well, either way, it doesn't really matter if I had this constant inside of the parentheses or if I did something like 5x plus c3, because this constant, all it says is that it's a constant value, right? If I were to scale a value, if I were to scale this, like in this case, the only difference between this case and this case is if I were to expand this, I would get, so the expanded version of this is 5x plus 5c3, and 5c3 and c3 in my eyes is the same thing, right? If I scale a constant by 5c3 or by like 5, I can just call that c4, and to me that's just another constant. And so you can kind of be loose on where you're putting these constants, because all they're representing at the end of the day is like one numerical value, and it's not representing a variable. And so you can scale constants by any value and it's still going to be a constant, and as long as you have that property retained, you're fine. And because of that, if I were to like add up all these constants, I would get like c1 minus 2c2 plus 5c3. Or if you did your integrals another way, you might even get like c1 plus c2 plus c3. Doesn't matter what you get. But in the end of the day, like the summation of constants and like scaled values is just going to return another constant. So I can simplify all of this into just one final constant and remove all of this like specific C1, C2, C3. So I hope you see that, and that's why I wanted to split this up so you could kind of get this intuition about what constants are and what they represent and when we can manipulate them and remove them and do things like that. But getting back to the original problem, simplifying what we have ended up with, we get x cubed over 3 minus 2 times x squared over 2, which is just minus x squared, plus 5x. And like I said, all the constants just add up to that one big constant, because at the end of the day, it represents the same thing. So that's our first basic example of an antiderivative and evaluating an indefinite integral. With that in mind, I want to give out integral formulas, and those will help you quickly solve and evaluate various integrals. So these are integral formulas. And it basically becomes pattern matching at the end of the day. So let's just start. So if we have the integral from x of n dx, so notice how this is a power function. That is simply equal to x of n plus 1 divided by n plus 1 plus c. And note that in this case, n is not equal to negative 1. When n is equal to negative 1, so n is equal to negative 1 case, we actually have something else. So when n is equal to negative 1, what we have is like 1 over x dx, right? Because this is x to the power of negative 1. That actually evaluates to the natural log of absolute value of x. Remember the absolute value because that's important, times c, or plus c. So those are our two integral formulas involving power functions as our integrands. Now let's do one involving the exponential function. So the integral of e to the kx dx is equal to e to the kx divided by k plus c. And if you guys want to see like where these are coming from, and they seem a bit arbitrary, my best advice would just be find the derivative of each of these expressions, and you'll see that you'll end up getting back the integrand. And because of all the ways that we have sort of defined and motivated what an integral is, hopefully, and well, all of this relies on the fundamental theorem of calculus. Like, you'll see that this satisfies the fundamental theorem of calculus, and so these are valid mappings from the integral to what the evaluation of that integral is. All right, so we did the power function. Now let's do the sine function. So integral of sine kx times dx. K is again a constant. is simply equal to minus cosine kx over k plus c. And again, I don't think I explicitly mentioned this, but the reason why we need all of these plus c's is because, well, actually I did mention it, but when you take the derivative of a constant, 0, and so there can be infinitely many functions that satisfy this integral because of the fact that you can have a 0 derivative, and you can place any value of c over here. So you just have to make sure that we're mathematically correct and we satisfy all the possible values that once you take the derivative of this, you get back this. You need that plus c. All right, now let's go to cosine. So cosine kx times dx, the integral of that is simply equal to sine kx over k plus c. Number 5, integral of secant square x dx, that is equal to tan x plus c. Number 6, integral of cosecant squared x dx is equal to minus cotangent x plus c. Number 7, integral of secant x tan x dx is equal to secant x plus c. Number 8, integral of cosecant x cotangent x dx is equal to minus cosecant x plus c. And so these are basic indefinite integrals formulas, and they'll help cover how to evaluate a lot of different integrals, but they won't help with all of them. Some of them require more tricks, and we'll cover them later. But let's just use these formulas to solve some problems. So example 2. Let's say we have the integral of 1 over square root of x dx. We can rewrite this as x to the negative 1/2 dx, and you can see that this is again a power function. So this simply evaluates to x to the negative 1/2 plus 1 divided by negative 1/2 plus 1 plus c, and that the denominator ends up becoming 1/2. Similarly, this is 1/2. So we have x to the 1/2 divided by 1/2, but that's just multiplying by 2 plus c. You can rewrite this as 2x or 2 times square root of x plus c if that's the form that you like it as. So that's the first part of that example. Another part of that example is just evaluating e to the minus 3x dx. And this comes pretty clearly from our formula, and this is just e to the minus 3x divided by minus 3, which is negative 1 over 3 e to the minus 3x plus c. Finally, let's just do one with trig functions. So cosine of x over 2 dx, that is sine x over 2 divided by 1/2, same as multiplying by 2, and then plus c. So yeah, solving for integrals, really not too bad after you kind of have the common integrals in your head, and that should basically come with practice.